Well, because I was with you in there, and I just not. I closed my eyes for a minute. Like 45 minutes later, I woke up. I was like, oh no. We had a good time. We went to Big Battle shots.
The joys of student life, sort of, isn't it?
Yeah. To touch of it before we go back to regular life.
Sorry?
To touch of it before we go back to regular life. So, it's not the same.
No.
Were you a party person during
God, no.
During your younger days?
No, absolutely not.
Did you go to university in Germany?
Sorry?
Did you go to university in Germany?
Yes, I did, in Munich. And
You were at the top of the town.
Absolutely. Absolutely. I actually stayed at home because it was so much cheaper. So.
That's fair, actually. That's really fair. That's most of us.
Well, I mean, it wasn't a big deal because I'm not a party person anyway. I think the first time I probably shouldn't say that, the first time I ever entered a nightclub was at the tender age of 40. Yeah.
Dropping one of your kids.
No, it was in Indonesia.
It was where?
In Indonesia. Yep.
Okay. And why did you go? Just because? Why not?
No, my then wife, did a PhD there, and she said, and I visited her, and she said, "Hey, let's go to a nightclub." And I was, okay, why not? Never been to one, so why not?
What was your experience?
It was
In all words.
interesting.
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 I thought you would have said loud.
It was fairly loud, although perhaps it was the wrong time. We were there at 10:30.
That's highly.
Probably that was the reason. So there were probably 30 men. Okay. And I think my wife was the only female. So I wasn't quite sure what the etiquette was. Yeah. So no excessive student life. I'm terribly sorry. And I just realized I'm recording that.
Yeah.
Which is not a good thing. So what happened to the rest? 6, 7, 8. That's good. They're coming good. So do you have the day off tomorrow? Or do you have to go back to wherever studying tomorrow?
Yeah. Friday's usually our study day.
Oh, so you have one day a week?
Yeah.
Aha, I see. Good morning.
Okay. Fair.
Uh-huh. And the apprenticeship, that works for you guys.
Yeah.
So I think you save a lot of money, don't you, in terms of tuition fees and then you also get a lot of, sorry? A lot of effort. What do you mean?
In my opinion, we save a lot of effort. We don't have to
save
come
a lot
in
of
for, we don't have to go in for lectures or.
But you have to go to work.
Yeah, we have to go to work.
That's separate.
And you get
I
paid.
find work a lot less effort. It's like, and now.
We work from
Actually,
home
I'm
most of
doing
the
it.
time. We only go in the office once every 2 weeks for our company.
Yeah, I work from home. That's not really what it is. Though. It's just more like.
Really?
It's easy to do work.
Okay.
But a lot harder to.
Fill me in. Fill me in. Why does not everybody do an apprenticeship?
Not a lot of people do know that still. And it's very competitive. Yeah, there's only a few spots.
And the government can't afford it.
Everyone can't afford to pay for everyone.
But also a lot more time it's looked down upon because everyone's going to university. It's better. Yeah, because you say, oh, I'm doing an apprenticeship, they think you're really stupid. Yeah.
I agree.
Really?
Yeah, because before, like, a few years ago, apprenticeships were only for like hairdressers or like people that can get higher education.
You can only get like BTEC.
Yeah.
Stuff like that.
But you just say, but you just said they are very competitive.
Yeah.
Yeah. So my immediate reaction was, wow, I'm dealing with a bunch of elite kids here, right?
I describe myself like that every morning.
Yeah, you say, yeah. In the mirror, right? I usually say, I don't know you, but I will still wash you.
No, but yeah, it's like competitive. The government can't afford to give it to everyone. It's not always apprenticeships. There has to be an apprenticeship standard for a specific job.
I see.
So you can't just say, for example, I don't know, what is there not an apprenticeship standard for mechanical engineering? Let's say you can't just say okay. So be somewhere
Pure mathematics.
Okay, yeah. Pure mathematics, right?
How would you do an apprenticeship with that?
Exactly. Like,
Yeah.
it doesn't work with every
So
degree.
it doesn't
Yeah,
work.
I see.
If you can merge it with a degree.
Yeah, I see.
In Germany, apprenticeships are way more standard, right?
In Germany, apprenticeships are very, very common. If you don't want to go to university, you do an apprenticeship, and usually most companies take apprentices on.
But do they pay for it? The company pays for it?
The company pays for it. Bless you.
Is it through government?
It's not funded by the government. It's funded by the company.
It's funded by the taxes.
But usually you don't have a degree associated with the apprenticeships in Germany. You are just you get a sort of a qualification afterwards. Yes. So you do your apprenticeship for 2 or 3 years or something like that, and then you have a certificate in that particular area.
That exists here too, but then we also have degree ones.
Yeah. I think you probably, but in Germany, with the apprenticeships, you always have to attend sort of classes as well,
Right, yeah.
which is compulsory. So it's basically a dual approach. You get the hands-on practice from the company and also the additional skills. And it's not, sometimes it's just 1 day a week or something like that, but usually it's done in blocks. So you work 3 months in the company, and then you have, say, 2 weeks or 3 weeks where you have focus on school. Yeah.
Some apprenticeships that work like that. One of my mates is electrical engineering apprenticeship, and the way they do it is rather than 1 day a week you do surgery, they do it once every 3 months. He has to go to uni for a week.
Yeah, absolutely. Yeah. But it's usually not done at university. It's done
like
at
college or something like that.
it's a sort of a college. Yeah, exactly. Yeah. And I think more and more people realize that probably a university degree is not necessarily for them, and that the apprenticeship really focuses on, yeah, well, a lot of hands-on and practical skills in a particular sector, which is, I think, which is a great idea. So,
It's not for everyone.
yeah, you're doing the right things, in my view. Okay, shall we make a start? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's more than half. So we make a start, okay? And the rest hopefully will join us. Good morning.
Good morning.
Sorry, I put the thing up, but
Oh, thanks.
sorry. Right. Last push. We get through that today. And correct me if I'm wrong. Yesterday afternoon, you did some gene analysis.
We were supposed to, but the portal didn't work. The website didn't work.
Well, for us, it seemed like we didn't have access from Moodle. So every time we all tried to load it, it just came up as an error message. At first, it was taking time for you to sort it out, but obviously.
I tell you what. What a shame, right? I tell you what. In this case, why don't we do a little bit of gene analysis today with statistics? Let's see if that works. Good morning. No worries. No worries. No worries. No worries. Why don't we do that with statistics? And
Thank you.
so yesterday we discussed working with discrete data. I showed you this Poisson distribution, and we will come back to that as well, because we still have one big question open, and I know you are absolutely dying to get an answer for that. And that relates to column. No. That relates to, the life of your unborn child.
Oh,
Right at the beginning, yeah. We need to sort that out, because this is a sort of a cliffhanger and can't let you go with big question mark. So we will come back to that. I showed you how we can work with proportions, and what I'm going to show you today is, again, we are working with discrete data, but this time these data are sort of, again, they are counts, but we need to apply some slightly different methods with these data, as you will see in a moment. So let's assume this gene analysis yesterday would have worked all right. And of course, you all know what a gene is. A piece of DNA that contains some information, whether this is information for a protein or something else. We don't care at the moment, we just simply say it's a piece of DNA. And the DNA is made up of what? Of what is DNA made up of? Bases. Exactly, you are absolutely right. So you've got a base attached to a sugar, in this case a deoxyribose, and the sugar is connected by a phosphate to the next base, right? Absolutely right. How many bases, how many different bases do we have actually? No, just don't worry about the base pairs. How many different bases do we have? 8? 1? 4? 4. Okay, yes, we have 4 bases. Don't worry about names. What are they abbreviated? Yeah. A, T, C, and G. Adenine, thymine, cytosine, guanine. Right? These are the 4 bases. And they make up the entire human genome. How many bases do we have actually? In terms of a human, how many? Well, they always come in base pairs. How many base pairs do we have? Many, many, many. Yeah? How many, many, many?
Millions.
If you've got million bases, you are probably at the evolutionary stage of a virus. Okay, so you're absolutely right. We are talking about roughly 3 billion. And that's quite a lot, right? But it contains all the information. It's the blueprint for you and everything that makes you, that determines your height, your hair color, your skin color, your eye color, everything, your susceptibility to diseases, for example, your immunostatus, whether you are allergic to bananas or something like that. This is all encoded in the genome. So we've got 4 bases, and let's say we have a particular DNA sequence. I just make one up, say A, C, T, G, T, T, A, C, A, G, G, C, A, whatever. Yep. This would be a DNA sequence that we probably find quite commonly in these 3 billion bases. And this contains the information for, let's say, an important protein that determines, I don't know, your skin color, right? Now, of course, if you change one of these bases, it could, but it doesn't have to, it could change also the protein and the protein's function. And just by simply changing one base, you can envisage that you might end up with, let's say, a different skin color, or you might actually end up with what is called, these mutations are called, these changes are called mutations. You might end up with, cancer or something like that. Very typical or classical example is one of the genes, the BCL5 gene, or no, BCL1 gene, I should say, BCL1 gene that is related to something called BRIC1. Famous gene, which makes you very susceptible to breast cancer. Very famous case about that. I don't know whether you are aware of that. A famous actress discovered that she had this mutation. Who was that?
For breast cancer?
For breast cancer.
Oh, okay. Angelina Jolie.
Angelina Jolie, absolutely right. She discovered that she has inherited this mutation of this breast cancer gene. And in order to sort of avoid this very aggressive case of cancer, she went for a double mastectomy and had both breasts removed. in order to, make sure that she does not develop breast cancer. Turned out, which was not known at the time, this mutation does not just affect breast cancer. It can also affect a lot of other tissues. So while she's probably not going to die of breast cancer now, she has not totally avoided the situation. But it's probably, it protects her. Anyway, what we are going to do is we are looking, for example, at one particular position here. Let's say we look at this position here, and we check out lots of different people, whether they have in this sequence, everybody has more or less this sequence, do they all have the same sequence? This could be here the sort of the thing that decides whether you have breast cancer or any other cancer or not. Okay, so what we might see, and I hide this from our column so that he doesn't get PTSD when he sees the word chi-square. What we might see is we look at 100 people. I think this is 100. Yes, we have 100 people. And we ask the question, what base is actually in this position here? And we find that out of these 100 people, we observe 20 people that have an A in this position, like I've drawn here. They have an A. 30 people have a T. 25 have a G, and another 25 also have a C in there. And in total, we've got 100 people that we looked at. It's a fairly small sample, but for our purposes, it will be absolutely fine. So it tells us that there is a certain variability in this position. And we can now ask the question, is there any preference for a base in this particular sequence? Is any base preferred by nature over the other bases? So out of the 100, 20 A's, 30 T's, 25, 25. What is your gut feeling? Is any of the bases sort of preferred by nature? It has goes, yeah.
I don't know. I don't think so.
You know what I'm looking for. What the question means, yeah.
Yeah.
Is A, let's say, is A overrepresented? Is A very common? No. Is T common? Yes. So does that mean that T is actually a base that we would find more often than, for example, A? What do you think? Not necessarily. You have learned to be very careful with me what you say, right? It depends, not necessarily. I want to sit on the fence, right? Okay, so it looks like that T is more common than A. You're absolutely right. Looks like that, but not necessarily. Now, how can we actually figure out what's going on? What would we expect, actually? These are our observed data. What would we expect if it was not at all any preference, how many people would we expect?
25.
25. Why do you say 25?
100 divided by 4.
100 divided by 4. Where does the 4 come from?
4 base pairs.
It's 4 base pairs. And if we assume that there is no preference, we would just simply say it would be 1, 2, 1, 2, 1, 2, 1. Yeah? So we just have 4 parts, and we would expect 25, 25, 25, and 25. And again, we've got our 100 back. Now, of course, sometimes it doesn't always have to be 1, 1, 1, 1. There could be cases where we would expect something like 1 to 2 to 1 or something like that, or 1 to 2 to 3 or something. It depends on basically the question what we're looking for. But what we see is, we would expect 25, but we only see 20 for the A. And with the T, we would expect 25, but we see 30. So it could mean that there is an overrepresentation of T's. And with the G's and the C's, they are pretty much where we want them to be. There's nothing exciting about it. But it's the A and the T's that sort of make us a little bit wonder whether there is a bias, if you like, towards T. And A is a little bit selected against. So how can we figure out whether this difference between the observed and the expected data is actually something that is a true effect? Let's not forget, this is just a sample of 100 people. And of course, we would like to know, is that true for the whole population? So we have a sample, and we are trying to figure out what happens in the population, right? So how can we actually analyze that? The answer is very simple. We perform what is called a chi-square goodness of fit test. Why is it goodness of fit? What does that mean? Well, we have proposed a model. Our model, in this case, is a representation of what we think. The model is 1 to 1 to 1 to 1. That is our model. That is what we have in mind. That is our expectation. And now we test whether the observed data are statistically significant different from this model. And of course, what we are going to do is we do hypothesis testing. Surprise, surprise. Yep. So the protocol is we need to formulate a null hypothesis in the first place. Have a think about it for a moment. What could be a null hypothesis in this case? What could be a null hypothesis? And think about the wording again.
There is no significant difference between the number of
Yeah, good.
the number of bases in the genome in the population.
You got the gist pretty much right because you used the word population in it. And that's really very good. Well done. Now, what we are basically saying is there's no difference between the observed and the expected counts in the population. Any differences that we can see in our sample can just simply be explained by sampling error. And you see, it's the old boring chestnut that it's always the same thing. And we can formulate the alternative hypothesis. There is a difference, and there should be an S. There is a difference between the observed and the expected counts in the population. The differences that we see in the sample cannot be just explained by sampling error, that we were just unlucky and got 30 people with a T instead of 25. And there is apparently a true effect, a true preference for T or selection against A. Next step in the hypothesis testing, of course, would be we set our significance level alpha, the type 1 error. We set that to 5%. There's no reason why we should do something differently. And we make our decision rules. P smaller than alpha, H naught has to go. P larger than alpha, we fail to reject the null hypothesis. If we do reject the null hypothesis, we just simply run with the alternative hypothesis. Exactly the same. It is just the wording of the null hypothesis in this case. Yeah, very simple. Next step, we need to calculate the p-value. And we need to calculate a test statistic. And luckily, this test statistic is not terribly complicated. The most complicated thing for this test statistic is actually to find the right symbol on a computer, because the test statistic for that is abbreviated with the letter chi, Greek letter chi, which is sort of a slightly pissed X with wobbly legs. Yeah. But effectively, it really means it is an X. And it is also then usually squared for whatever reasons. We don't need to go into that. So that is the test statistic, which is called chi-square. Like I showed you before, we can calculate a t-statistics, and that is basically exactly the same thing. So how do you calculate this test statistics? The equation for this test statistics, don't worry about the square, we will never take the root of that. It's just simply an expression chi-squared. How do we calculate this test statistic? It's not terribly difficult. What we do is we take the number of observed minus expected, we square that and divide by the number of expected. observations. And then we add them all up. That is basically what this chi-square does. So how can we do that? Very simple. We just, well, we add a new column here. And we say our observed is 20 minus the expected, that is 25. We square that and divide it by the number of expected, in this case 25. Yeah? So for the next one, for the t, we have 30 minus 25 squared divided by the expected, that's again 25. For the g, it is 25 minus 25 squared divided by 25. And for the c, it is also 25 minus 25 squared divided by 25. Yeah? Very simple sort of algorithm that we use. And now we calculate that. What is 20 minus 25? Minus 5. What happens if we square it? It's 25. You're absolutely right. 25 divided by 25? 1. Absolutely right. What is 30 minus 25? 5. What happens when we square it? 25. What happens if we divide it by 25? 1. What do I get for G? 0. And for C? Same. Also 0. Okay. And when I add them up, what do I get? 2. So the chi-square value equals 2. Okay. The chi-square distribution that we would use for that is very much like the, looks a little bit like the Poisson distribution. It's not symmetrical. And there is a whole bunch of these distributions, like the t distribution. So in this case, it probably looks a little bit like that. And what we need to do is we need to pick the right distribution and say, what is the probability of finding actually a value of 2? Let's say this value here of 2. What is the probability of finding this value of 2 if we have this distribution that represents the distribution of the null hypothesis? And in order to do that, to pick the right distribution, we need to, again, talk about degrees of freedom, because that is what defines these distributions. And we said the degrees of freedom, in this case, is defined as the number of different observations that we can have, the number of different bases, if you like, minus 1. So that would be n minus 1 that we have done before. So we've got 4 different bases. Yeah. What's the degrees of freedom? 3. So we've got chi-square equals 2 with 3 degrees of freedom. Yeah? Happy with that? So is there a calculator, a convenient calculator, an online calculator that we could use? Answer is yes, but I'm not going to show you because otherwise that goes wrong. It has too many options, unfortunately. But luckily, we can use Excel with this equation here. It's a function. It's a chi-square distribution function. And we are, in this case, only looking at the right side. So in a way, these chi-square tests are usually one-tailed by default. And this function takes 2 arguments. The first one is the calculated chi-square value that we've did, that was 2, and the degrees of freedom, that is what we had with 3. Yep, happy? Easy. Let's see if we can do that. I need a spreadsheet. Let's do this. Okay. Have I done that? Oh, yes, I've done that already. I've put that in. You probably see it down here. Chi-square dot dist dot rt 2, 3. And that gives us a p-value. So here the p-value is 0.57. Yeah, very simple in Excel or in any other spreadsheet. So we can say the outcome of that, p equals 0.57. Now, we set our significance level alpha to 5%. What do we do with the null hypothesis? Reject or fail to reject? Loud?
Fail to reject.
We fail to reject because p is larger than alpha. If p is high, H naught can't die. Right? So we fail to reject the null hypothesis. And we say there is no difference between the observed and expected counts of the bases in the population. The only difference that we saw here, the 20 compared to 25, what we would expect, or the 30 in relationship to the 25 that we would expect for the t, is just simply due to sampling error. It could happen again, but there is actually no true difference. There's no preference for any of the bases in this particular position of the gene. So it doesn't matter really. There doesn't seem to be a real preference for one of the bases. Yeah, makes sense? Chi-square test, goodness of fit test. Right. Now, of course, I told you a little bit about cancer and mutations. So if you've got some nasty mutations, they could very easily lead to cancer. But we are not always very clear about the link between a particular mutation and cancer, just simply because we've got so many bases, and very often things influence each other. Yeah. So, for example, this BCL1 gene is even if you have the mutation, it does not necessarily mean that inevitably you will develop breast cancer. There are lots of other genes that can suppress the function or alleviate the function of this gene. So, and therefore we are very often not totally clear whether a particular mutation will inevitably lead to cancer. But for our next example, this is exactly what we wanted to find out. Let's say we have a mutation where we think, there could be something in it. It could lead to cancer. And I don't know whether this is, and I'm looking at Helen, whether this is now a sort of common practice in clinical studies or drug designs or something like that. Do people look at gene sequences?
I have no idea.
No idea.
Sorry.
My suspicion is that this is something that is coming in the future, where people then, even for eligibility criteria, when you enter a clinical study,
Sorry, they do that.
yeah, they do that.
in
That
oncology.
that they look at, for example, certain markers and say, ooh, we know you have the breast cancer gene. We are looking for a drug that does something that helps, that suppresses. So you are a top candidate for our study. So yes, we want to enroll you. Or, oh God, you're one of these boring people. No breast. We could still use you as a negative control for that. But you know, they're pretty boring. But count yourself lucky that you are not amongst the positive things. Okay, so let's say we do a study, again, a fairly small scale study, where we look at a mutation and at the same time we look whether the person has cancer. So what we are trying to figure out is basically, is there a link between mutation and cancer? So what we find is that out of this number of people with the mutation, 20 develop cancer and 80 don't have cancer. On the other hand, if you don't have the mutation, 10 will develop cancer and 90 don't develop cancer. And our question now is there a link? Is there an association between mutation and cancer? What's your guess? Always start with, try to guess what might be. Do you think there is a link between cancer and mutation? Or is it just simply down to sampling error? You say no.
Well,
Again, you are sitting on the fence.
I think that's sampling.
A sampling error.
Yeah.
Okay, good. Anyone disagrees? It could very well be sampling error. Let's see how we can do that. Now, what we need to do in the first place is, well, we need to develop a model. But this time it's not sort of just one-dimensional. Yeah, it's two-dimensional. And what would be our model, actually? It's a little bit tricky. Well, actually, before we do anything, let's just simply do what is called calculate the marginals. The marginals are the numbers that are sort of in the margin of this table. This is actually called a 2x2 contingency table. And we worked with something similar when we did with the errors, for example. So it's very similar. So all we need to do is we just simply calculate the numbers of how many people have the mutation. So that's 20 plus 80, so that would be 100. And without the mutation, we have 10 and 90, so that's also 100. Oh, well, that's quite good because we don't have to fry our brains as nice numbers, but it doesn't have to be the same numbers. It can be any number. Now we can also do the row marginals. So we've got 20 and 10, that gives us 30. And 80 and 90, that gives us 170. And we can also calculate the gross marginal, that is overall. And the gross marginal must be the same when we do the row marginal, this one here, and the column marginal. It must be the same. It's a good way of checking whether this actually is true. So we get 100 and 100 gives 200, bless you. 30 and 170 gives also 200. So that's the gross marginal. Okay, so we've defined the marginals. And what we can do now is we can sort of do a little bit of, I think probably the correct term would be to do some conditional probability, but I don't want to scare you with these terms. We can now actually calculate how much in each field, how many people we would expect. And the way you do that is you basically multiply, if we look at the first cell here, this one here, if we look at that, we take the column margin, multiply it with the row margin, and divide it by the gross margin. So it is this and this. So that would be 100 times 30 divided by 200. That gives us the expected number. Okay? We can also do the same thing for the next cell down there and use exactly the same method. We can do 100 times 170 divided by 200. Now, for this cell here, We do the same principle. 100, 30. So that would be 100 times 30 divided by 200. And the last one, again, that would be 100 times 170 divided by 200. You see the principle that I apply? I use the margins or the marginal numbers to calculate the expected numbers. Yeah? And it's not terribly, how shall I say, sophisticated, the whole thing. It's rather straightforward. So what we do is we just calculate this number and say we have 100 times 30 divided by 200. What does that give us? So 100 divided by 200 is half.
Oh, that's clever.
Half of 30 is 15. Yeah, 15. So we would expect 15, but we see 20. 100 divided by 20, 100 divided by 230, that's 15 as well, isn't it? That's expected here. 100 times 170 divided by 200 gives 85, right? It is just simply 170 divided by 2. And for this one, we also have 85. Yeah, happy? Fantastic. So this now gives us our expected numbers. And we can now use that and write and calculate our chi-square score for that. And we do that in exactly the same way that we have used before. We set chi-square equals the sum of observed minus expected squared divided by expected. And we have, what have we got? Oh, actually, what we should have done before we get trigger happy, what did I forget? The protocol. Yeah, forget the protocol. You always start with the protocol. So the protocol would be, there is no difference between observed and expected counts in the population. Any differences can be, wait a moment, we've said that before, didn't we? Yeah, but it's the same thing. It doesn't change. That's probably why I skipped it. There's a difference between observed and blah, 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 yada, yada, yada. And what would we do next? If we've tried to devise the protocol, what was the next step? Step 2? Alpha, exactly, alpha equals 5%. Decision rules, p smaller alpha, adios, p larger alpha, we fail to reject. And now we calculate chi-square. Okay, so let's do the chi-square. So we have, for the first cell, we have 20, that's our observed, minus 15. Yeah. Squared divided by, what do we expect? 15. Okay? Plus, doesn't matter which way we go, we can go from left to right. We can say we go for this cell here. We have plus 10 minus 15 squared divided by 15. Plus, then we have the bottom left, we have 80 minus 85 squared divided by, what's the expected? 85, absolutely right. Is a new expected plus 90 minus 85 squared divided by 85, absolutely. And now you have to do a little bit of maths. So 20 minus 15, that's 5 squared, that's 25 over 15. Plus, here we've got the same, 10 minus 15, that's negative 5 squared is 25 over 15. Plus, that's 25 over 85. Plus, that's also 25. Oops. 25 over 85. Yeah. So we have, what have we got? We have got 50 over 15 plus 50 over 85 equals, can't do that in my head. Can somebody activate a calculator, please, for me? 50 over 15 plus 50 over 85. Oh, let's do it quickly. Where are we? 50 divided by 15 plus 50 divided by 85 equals 3.9. Yeah? Do you get that? Good. So we've got 3.9. And that is our chi-square value. So chi-square equals 3.9. Now we need to figure out the degrees of freedom because we said we need that for the calculation. And this time we have not just one-dimensional. What happened?
Just check my phone to see if I've got a message saying, can I have a laptop charger?
We're good to give me it now. It's fine.
Hold on.
There was a laptop charger earlier here. There was yours. You left it kindly. Okay, good. So how do we figure out the degrees of freedom? Now we don't have just one row. We have rows and columns. And the rule is, if you've got something like that, the degrees of freedom equals the number of rows minus 1 multiplied by the columns minus 1. And that refers to the data that we measure. It does not include the marginals. So we have 2 rows, cancer, not cancer, and 2 columns, mutation, not mutation. Yeah? So we can calculate the degrees of freedom. That would be 2 minus 1 multiplied by 2 minus 1 for the columns, and that gives exactly 1 degree of freedom. Yeah? So what we need to do is equals chi square dot dist dot rt. We have 3.94 it was, with 1 degree of freedom. Let's see if we can do that in our calculator. I just simply modify that because I'm lazy. And I know what happens if I type in things. So we have 3.94 with 1 degree of freedom. Looks good. Okay. That is right. And we get a p-value of 0.047. Let's write that down. P equals 0.047. We reject because 0.047 is smaller than alpha, 5%. We reject the null hypothesis in favor of the alternative hypothesis. Yeah. This means the number of observed cases is different from the number of expected cases. And the expected cases would be if there was no association or interaction. Sometimes people call it interaction between the 2 factors. So the verdict is difference between observed cases and expected, which indicates there is an association between mutation and cancer. So we have shown that apparently this mutation might be linked to cancer. which I think is a very interesting finding, and in a way is probably quite, oh wow, cool. Because let's face it, our involvement in calculations, the mathematical side was rather limited, I would say. It's not terribly complicated. Excel does all the heavy lifting for you anyway with the p-value, and just by looking at by taking these data, we can already say there is a good indication that this particular mutation might be linked to cancer. Yeah, happy with that. But it's only a p-value. It's only a p-value. It just tells us, are you pregnant or not? How dangerous is this mutation actually? I tell you after the break. 10 minutes, okay? Any questions? I've killed you.
Right, the coffee shop is not open, so I'm going to Narrows for a coffee. It's a bit further away. Do you want anything?
Oh no, thank you. That's fine. Yeah, I've got water. I know the fish.
I need my coffee.
I've just told insomnia. I've just told cured insomnia. If you can't sleep, just try and someone sleep. That is rough. Been there.
We're just lazy.
Just staring at the roof, and then eventually you're just like, well, if I'm suddenly awake, I might as well call my phone.
Well, yeah, and it's like my eyes just like burning. And I was like, oh, great.
Sorry, I messaged you first. You replied, I haven't been to yeah, and then eventually it's too expensive. She has carrots. That was disgusting. They had just been in her mouth. It was still like wet, but cold. Shoved it right. So I'm telling you like this. She was like, actually, the real curtain off because my head is back. Yeah. So I was like, oh, no, I need you come up. Shower. Oh, me. Me. I was like, relax. What about now? I don't even think she's coming to the room because apparently Professor said before they went on holiday, she's like, remember, you get like 10 days where you can keep in touch with work or whatever, so you can start going back, like, or doing your house or something before your maternity leave. So she said she's going to be with a manager, healthcare, they would want to do it managers over it, and they want a certain day each week. If they say Friday, would my mum be okay with it? If my mum wants, I would be okay with it. No, my mum wants Friday.
At least she asked. Yeah, at least she asked. Like,
When
when
mum was going, she was like, I don't know if I'm going to work for.
the bill became that. Because it's feel like if you have like if the bill's not that much, you should more care basic bills and all that. I think the rest
I get also like someone's doing and I know my brother. Dad took care of it. I think that we once a year, twice a year, to tell me he's going to freeze.
not this, just do something else. You can help you to get your bills.
Yeah, that's what it is. So you must keep that on.
But it isn't up to what the increase is the.
I don't know. Yeah, I mean, one was today.
I think
And also when she does that, but she doesn't know.
but also, he doesn't have to go through the town. She could put an issue, other than that, he knows that's all. Okay. Okay, I'm listening.
You didn't want the baby, you didn't say you were going to
I'm not have to be, but I mean, I mean, I can. And then, yeah. I was not good. We want to go to, another one, the country was the tea, which one? Another, Morocco, Libya, Senegal, and then one Egypt. And I forgot the name. No, they took, not Turkey. Tunisia, that's the one. The model here right now,
Yeah, but it's not all that.
but they just like she could if it were not they kind of feel I think she had two and had to carry everything.
Yeah.
But she did it very, very well.
Yeah, I know the people. Every time we have people around, we tell them first what to do.
Because I knew I was the only one in there. But I was like, yeah, well, like,
Have you sorted out the charging problem?
Yeah. It's just because our message panel works, but you don't see the message. So we see it now.
It's just too long without it.
Or to do this stress factors?
Is it easy?
it's everywhere.
You've done it. So is it like easier to navigate?
You see the video? There's a video on TikTok where you literally get really bad. You literally see like
What you are asking.
You have a what? Sorry, say that again. Yeah, I've said that before.
I've got a YouTube channel.
That actually is really weird.
Huh?
That actually is
PK11
Oh, the and to the side.
I just feel that's why.
It's too distracting.
Really
interesting. Watching people
Oh, no.
Unlike
I take it Snapchat is still a thing.
Yeah. I don't think it's as big as it was.
TikTok, Snapchat,
I never even.
yeah.
Facebook. No, Facebook is for old people.
I used to use it.
Are you okay?
Facebook Market.
Yeah.
Insta,
Yeah.
everybody's on
This
Insta.
morning, and then just.
And of course, WhatsApp, right?
Sorry, I did it all.
Yeah.
And then this, perhaps, one thing I just got this map on, the other you still chase. Please remember to say hi.
That's so good. Oh no. No, you put that as
She messaged me.
I mean, I would. I don't really have a car though.
I don't, because you're not meant to be working.
We're missing a tall man.
13 is a bad number. I give them another 2 minutes.
And Nina.
That's why most American buildings don't have 13 floors, that right?
Hide it back and then she'll buy it.
Okay, now we are 14. then I can risk carrying on. I want to make two comments, actually. This sort of association testing or interaction testing is probably getting more and more frequent in clinical trials because there is sort of the idea of, well, if I develop cancer and you develop the same cancer, previously the idea was to use exactly the same treatment. But you probably agree that while we might have exactly the same type of cancer, like say, you know, pancreatic cancer or whatever, hopefully not, I'm not, yeah. We are two different people. We have a completely different genetic makeup, and therefore it would make sense to take that into account. And for example, a drug that might work on you might not work on me because with all the other genes that play a role, it could very well be that, you know, there is an interference with that. So personalized drug treatment is going to be the big thing in the future. It's called precision medicine, where you actually tailor your treatment, your drugs, your regime to exactly that particular person, and the information about this person is probably derived from their DNA sequence. You've got lots and lots and lots of data. But with lots and lots of data, you can basically feed that into some artificial intelligence or something like that, that then distills out the characteristic features, and it will, at least there's no doubt that this will happen in the future, will come up with absolutely personalized treatment plans for individuals. So this is a space to watch, and I think this is terribly exciting because it will impact everybody. So you will no longer do the bog standard trials where you have everybody receives the same treatment, more or less, drugs or placebo. It will be tailored towards the individual. And that makes it incredibly exciting and interesting. The other thing that I wanted to show you is what we had here, this contingency table, might be a little bit familiar to what we actually did yesterday with the proportion testing. And what we did in this chi-square table was basically we had this 2080 or 1090, and we then calculated the marginals, so 100 here. But of course, we could very easily just simply say, well, in the case of plus mutation, with the mutation, we can say 20 out of 100 developed cancer. So we could actually say plus mutation, 20 out of 100 had cancer. Whereas in the minus mutation, we found that 10 out of 100 had cancer. Yeah. So when we look at that, this is called actually, this 20 out of 100 is called actually a risk. That's the technical term. 20 out of 100 people have the risk of cancer with mutation, whereas 10 out of 100 have the risk without mutation. And of course, we could try and put that back into our proportions calculator that we had. Let's see if it comes up with the same result, whether it's 0.047 or something like that. Let's see if we get the same result. So I've put that in already, 10 out of 100 and 20 out of 100. It gives us the confidence interval, the 95% confidence interval for the individual risk. And drum roll, let's see what the p-value is. The p-value is 0.477. Very close to what we calculated with the chi-square. And that is actually why you find this proportion. Where did it go? Disappeared now. Just want to show you that. That is why you find this proportion under chi-square test, because that is basically what it does behind the scenes. The values are not exactly the same. So with our calculation in Excel, we got 0.0472, whereas this one gives you 0.477 or something like that. So it's a slightly different. That is something because this calculator adds a little bit of noise to avoid one problem. And I'll show you what the problem is in a moment. The problem is this chi-square test, it does not make any assumptions. So we had previously, we said, for example, the normal distribution or the t-test, it makes an assumption that it comes from the normal distributed population, right? That is not what the chi-square test does. It doesn't make any assumptions, with the exception that it says, when you've got such a table, a contingency table, every single number must be larger than 5. Now, in our case, this is easily the case with 20, 80, 10, and 90. But if one of the numbers is less than 5, or, if one of the numbers actually becomes 0, then the chi-square test just simply will not work. End of discussion. And so there are then other tests that people would have to do, but we don't have to worry about that. And the calculator for the online calculator actually tries to do a little bit of a trick to avoid this problem with the smaller than 5 issue, and that's why the numbers are not exactly the same. Okay, happy with that? Now, before the break, we said we see that there is an association. We see that there is an association, but how big is it? I mean, if you tell a patient, well, you've got the mutation, I'm terribly sorry, you've got the mutation. and this mutation is linked to cancer. How worried would you be?
Pretty worried.
Pretty worried, yes, absolutely. I mean, sometimes the doctors are a little bit more direct. They say, have you read Harry Potter?
Yeah.
Yes. Well, because if people say, no, I haven't, then the comment would be, don't bother starting. You won't come to the end, right? It will kill you before that. But should you be worried if you have actually the mutation? So you say you would be pretty worried. How likely is it that you will develop cancer? We can't say that from the p-value. P-value doesn't just, the p-value says, yes, there is a link. But how worried, how strong this link is, we don't know. And I introduced yesterday this effect size to you, this Cohen's d, or Hedges G, whatever. Cohen's d tells us, is there a big effect between the two samples, for example? And we can do a very similar thing in this case here. Is there, or I should rather say, is it likely, or how likely is it that you actually will develop cancer if you've got this mutation? I hope this never happens to you, although, having said that, 1 in 3 people in this room will, in their lifetime, have a brush with cancer. So it can, a bit sobering thought, but you know. But hopefully, treatment is getting better and better, and the survival rate will increase. How do we calculate this effect size? Well, the effect size is actually calculated in a very simple way. It uses odds. It's a little bit odd. What are odds? Odds in horse racing, absolutely. When you go to the bookmaker, you get odds.
You do.
Right? So what are odds? How do you calculate odds? So we had 20 and 80, that was plus mutation, and minus mutation, you have 10 and 90. So what are odds? Odds are just simply defined as number of successes divided by the number of failures. Right? When we talked about the proportion yesterday, we said a proportion that would be a risk in this case is number of successes divided by the number of total trials, which include success and failure. The odds actually don't look at the total number. It just says success divided by failure. And in this case, I mean, I wouldn't call it having cancer a success, but it is sort of counted, the event happened. So here, the odds for developing cancer, if you have the mutation, would be 20 over 80. Yeah? The odds of developing cancer if you don't have the mutation would be 10/90. Okay, that's simple. And that still doesn't tell us a lot, does it? Should you be worried? If I gave you the odds, 20/80, these are your odds. Doesn't mean anything, does it? No. So what you can do actually is we can formulate what is known as the odds ratio. And the odds ratio is very simple. It is just 20/80 divided by 10/90. This is usually abbreviated as OR, the odds ratio. And we just simply look at that. And now we get, if we put that into a calculator, I've done that here already, you would get the odds ratio equals 2.25. If I have not completely messed it up. So 2.25. Now that's the number, that's the odds ratio. What does that mean? Now it tells us something quite interesting. It tells us actually that in your case, you have a 2.25 higher chance of developing cancer if you've got the mutation compared to when you don't have the mutation. So your chance of developing cancer, the odds, go up by a factor of 2.25. Now, if previously we assumed it's not a very common event, the cancer, increasing your chance by factor 2 is still a little bit worrying, but nothing to worry too much about. Yeah? So this odds ratio is a good expression how much we should be worried about having cancer. And this is also, so the odds ratio is basically an effect size. Effect size for odds, if you like. It tells us how much we need to worry. Now, if you think about it, what does an odds ratio of 1 mean? Let's say somebody has an odds ratio of 1. What does that mean? Sorry, say again?
There's no significant difference.
There is no difference in the odds. Yeah, they cancel each other out. If there is more of that than that, your odds ratio would go up. If there's more of that than that, your odds ratio would go down. Yeah? If the denominator gets bigger, then the odds ratio goes down. What is the lowest value that the odds ratio can have?
0.0000000.
It could be 0. Yeah, it could be 0, basically. If the denominator is basically really big, then the odds ratio gets to 0. That means a huge emphasis on this part here. Big one, the odds ratio becomes almost 0. If this one becomes really, really small, what does the odds ratio turn into? You divide by something really, really small. It goes to infinity. You're absolutely right. Now, what we basically have is, when we look at these odds ratios, here we've got 0 when the denominator is very big. We've got 1 when there's no effect. And we've got almost to infinity when the denominator becomes very, very small, right? So when I look at that, it doesn't look very fair. This here is 1 unit, whereas this here is, up until infinity. So if I go to the bookmaker, and look at something like that, I would immediately go out again and say, wait a minute, there is a huge degree of unfairness. Now, there is one way we can deal with this unfairness, which you are going to find very, very commonly in clinical trials, because people do not report odds ratios usually. Well, sometimes they might report odds ratios, but what they do report is, I need to get a new page, sorry. I need to insert something. Oh, we just leave it like that. Instead, what they report is not OR, they report the logarithm of OR. And in this particular case, not the logarithm to the base of 10. They calculate, and I take that away. Now, yeah, are you going to do that? Yeah. They calculate the ln of the odds ratio. Is everybody familiar with ln? Natural log, yeah? Everybody, more or less? That's the logarithm to the base of e, absolutely. So that's the natural log that is very often reported, and that's called log OR, or the log odds ratio. What does that do? Well, if we take the odds ratio logarithm, what is the logarithm of 1? Loud? It's 0, absolutely. So what we get is our odds ratio. We had this image with 1, that was the odds ratio. With the log odds ratio, this now becomes 0. we have 0, and I probably should put that away, that's too confusing. With the log odds ratio, we have 0. 0 log odds ratio means no effect. And in a way, this is more intuitive, isn't it? If you say there is no effect in the odds, it would be 1 with the odds ratio, but it is 0 with the log odds ratio. Anything smaller than 0, when you log it, becomes negative, and this time it can go into negative infinity. Anything larger than 1, if you log it, goes into this range, and it can get towards positive infinity. Now we have got a very nice balanced sort of scale where we have our log odds ratio. So very often what you see in trials or in the literature, that people report an odds ratio. And there are also ways how you calculate a confidence interval for an odds ratio or a log odds ratio. But I would suggest that we leave that to the experts. Just as a sort of a footnote, we have calculated confidence intervals for means, but it doesn't have to be just a mean. You can also calculate a confidence interval of other things. And in this case, you can calculate a confidence interval of a log odds ratio. You can also calculate a confidence interval of other effect sizes like Cohen's d, and that is very often done and very often reported in the literature. But for the time being, we don't need to worry about that. Okay, happy with that? Brilliant. We have basically come to a sort of a natural closure of the discrete data. So I think we have early lunch. Back at, what is it, 12? Yeah, back at 12. And then we will do the last leg of it. And we'll look at something that probably will cause a little bit of, what the hell am I doing here anyway, right? So be prepared. See you after lunch, unless you have any burning questions. No? Thank you.